just to my laptop. All right. So yes, the title of my talk is quite a mouthful, sense of agency, attribution of intentionality, and joint attention in human-robot interaction. And I will be talking about these three topics, but I'll be actually starting reverse order. So I'll first talk about joint attention, then talk about intentionality, and finish with sense of agency. Let me just get this. Okay. So my background is cognitive neuroscience, as Tobias mentioned, and I use robots as sort of sophisticated stimuli to examine human cognition, social cognition specifically. And what we do in our lab most of the time is we translate paradigms from cognitive psychology into kind of more interactive scenarios like this one. So you see a human interacting with a robot. And while they're doing this, we record their EEG, we record their eye movements. Can you see my cursor, by the way? Okay, great. So you can see that this is a mobile eye tracking system. So we can see where the focus of attention is through measuring eye movements and neural activity. And we also give our participants tasks. So they need to, let's say, press a key with respect to a certain stimulus. So we can also measure their reaction times, error rates, and through that we can draw conclusions regarding their cognitive processes. So I'll start, as I mentioned, about joint attention, talking about joint attention. What is joint attention? It's a situation where if I direct my head somewhere and or point somewhere, if we were in presence, you would also attend to that same location because there might be something meaningful there, behaviorally relevant for you, for me, and we engage in joint attention, meaning we attend the same location in the environment at the same time. So this kind of concept has been operationalized in the lab by a modified Posner queuing paradigm. I'll very quickly go through this. Probably most of you are familiar, but just to be on the safe side, I wanted to remind what sort of paradigm we're working with. So Posner queuing is a situation where we experimenters queue attention of participants with an arrow, for example, and then there's a target presented in a queued location. So in this case, it's a validly queued target, or in the opposite location. And if this opposite location happens, then we assume that since attention was located where the arrow is pointing, shifting attention to the opposite location takes time. And that time is actually what we measure in reaction times to the target. So participants are usually asked to discriminate a target or localize a target. And in the validly queued condition, they would be faster as compared to invalidly queued. Now, what does this have to do with joint attention? Well, instead of arrows, we can also present social like stimuli. So, for example, gaze direction instead of the arrow. So it's exactly the same logic, but instead of arrow, we present gaze. And the idea here is that if participants follow the gaze of the agent, then you should see this effect of validity. So the difference in reaction times between valid and invalid cues. So we've done this kind of paradigm with a robot. And what you'll see is the robot will be directing participants' attention to one of the screens, embodied robot. So that's already, we can discuss that later because there's a lot of interesting methodological issues when you translate paradigms from screen-based paradigms that are very classical in cognitive psychology to embodied interactive setups. And there are many decisions that need to be made that make the paradigms not exactly comparable. So obtaining results that are kind of similar across our embodied conditions and screen-based conditions is already quite a success. So we have our robot directing attention of participants to one of the sides. And in addition, we present participants with a social manipulation, a gaze manipulation, where the robot either engages them in mutual gaze or averts gaze. And we wanted to see what does that actually do to attentional orienting in response to the gaze cue. So this is how the paradigm looks. The robot first engages in eye contact in this condition and then directs its gaze to one of the sides. So there's the queuing part, you see. And that was valid cue, now invalid cue, but still with eye contact. And now you will see averted gaze, so the robot will gaze down. And the question is, what does that mean for the gaze cueing effect? So having done this paradigm, just very quick, participants had to respond whether the target letter was a T or a V. So simple discrimination task. What we have observed is first, I mean, this was a whole series of studies. So we run many of those. And I will not go into detail in the entire series, but if you're interested, we can bring it up again in the discussion. So first of all, what we saw in our first set of studies behaviorally is that there was a larger validity effect. So this difference here is the validity effect in the eye contact condition as compared to no eye contact condition, meaning that participants followed the gaze of the robot more, so engaged more in joint attention after eye contact as compared to no eye contact. However, this pattern is not completely, let's say, always present. It depends on several factors, and it depends on the timing between the onset of the gaze cue and the target, the stimulus onset asynchrony, and that's something we can discuss in the discussion later. As I said, I don't want to go into discussion, into the details here. So the SOA matters and the validity matters. So the percent with which the probability with which the robot would actually gaze validly at the target location or not. So having said that, I'm now turning your attention to the ERPs here, because we locked the ERPs. So we measured EEG of participants while they were doing this task. And we locked our ERPs to target presentation. And this was our very first EEG study with the robot. And here I would like to stress that, as I said, methodologically, these things are very difficult, because for obtaining ERPs, you have to make sure that everything is synchronized well and that you have a very good control over timing, which is not straightforward with a robot. So integrating all these components, the EEG, the robot, the behavior of the robot, and the responses of participants is really not a trivial task. So basically, the take-home message here from this plot I wanted you to have is that we managed to obtain actually ERPs that would be classical ERP components related to Posner cueing. So this is P1 and N1 in the locked to the target, and what you see, the two curves is valid versus invalid cues, and we obtained validity effect in this case in both conditions. But interestingly, this is a validity effect that will be very classical in a Posner cueing. So we were extremely happy, because it was really our first study to see that you can replicate a pattern from screen-based stimuli to these sort of embodied scenarios. Now here what you see is in this experiment, we ran the same study, but with the eye tracking methodology. And we looked at fixation durations of participants during the mutual gaze of our averted gaze. And we saw that actually fixation durations were longer in the mutual gaze condition, which is, I mean, this is something one would expect, but it's also nice to see that indeed we can observe these effects in objective measures. And finally, the last plot that you see here, that is the EEG that we locked not to the target, but this time to the gaze of the robot. And what you see here is that there's more desynchronized alpha activity in mutual gaze, so the eye contact condition. And more desynchronized alpha means more engagement. So what we observe is that both in eye tracking data, in EEG, and in our also subjective reports, we also had subjective reports where we asked participants just to simply state whether they felt engaged more or less with the robot. We see more engagement in the eye contact condition, and that affects in turn the attentional orienting effect. So this is something that is, in a sense, expected. One would expect that, but if you zoom out a little bit, you might think, well, these are just two cameras of a machine, right? So our brain somehow processes this signal of those two cameras as an important, engaging social signal. And I can tell you just as an anecdote, subjectively, when you sit in front of the robot and it looks at you, it really does something to your system in a sense that it's really evocative. Which is very interesting because, again, I mean, these are just machines. So our brain somehow responds to this as a social entity. So mutual gaze with the robot is a signal that modulates joint attention and affects engagement with the robot at the level of subjective reports that I didn't show you the plots here, but I can show them later, and also neural responses. Now, having obtained these results, we thought, okay, let's do something more with the gaze, and let's have a more interactive setup and more, let's say, engaging setup. So we asked our participants in a completely, this is of course a different experiment. We asked our participants to play a game. It's a chicken game. I don't know if you know the chicken game. It's a really funny game. So you are seated in front of ICAB, in this case ICAB, an opponent, let's say. Between the two of you, there is a horizontal screen. And on the screen, one of you is operating, let's say, a simulated car, and the other one has another car. And the cars are going towards one another. And as they go towards one another, they enter an area at which everything gets paused. So you see here this gray screen, everything gets paused. And that's when you are asked to make a decision. Do you want to let your car continue, or you want to deviate? The chicken game comes from the idea of, do you chicken out and deviate, or you go straight ahead? If both of you go straight ahead and you crash, you both lose a lot of points. If you chicken out, but your opponent goes straight ahead, then your opponent wins, and vice versa. You see the payoff matrix here. So basically, it makes sense for you to do a little bit of a risky game here, but not too much. Now, the interesting part that we've done here is that during the moment of the blank screen, when participants were in the process of deciding, the robot either gazed at them or gazed away. So it was kind of like a poker situation, right? I'm just about to make my next move, and then my opponent looks me in the eyes. What does that do to my decision-making processes? So let me show you the video of how it looks, just so that you kind of see how much fun actually it was for our participants. So the cars go towards one another. Now there's the pause, right? You make a decision, the robot makes a decision. And while they're doing the task, we're recording also their EEG. And as they were making the decision, the robot looked at participants or looked away. Now what you've seen is, this was just for demonstration purposes, you saw the robot pressing the keys. We actually occluded the keys from participants, so they couldn't see which decision the robot made. But we wanted, so there was still, I mean, they could hear that the robot was actually pressing the key. Sorry, that was my music, that was not necessary. The robot was, they could hear that the robot was pressing a key, and that was important for us so that they knew that actually the robot is making that decision, as making a physical action on the buttons, but they couldn't see which one it was. So this is the first interesting pattern of results. What you see here is that participants took longer time to make a decision in the mutual gaze condition. And this was independent of probability of seeing one or the other gaze, because what you see here, 70% mutual or 70% averted, these are two groups of participants, and one group was presented with 70% mutual gaze trials. The other one was 70% averted gaze trials. And this way we made sure that it wouldn't be something that is related to frequency of observing mutual or averted gaze. So independent of which group participants were in, they were faster in responding in the averted gaze condition. So when the robot looked at them, they took longer. And we also looked at EEG during this period. And what you see here is the difference already in averted minus mutual gaze. And the little crosses here, this is where we have the region where effects were significant. And what you see here, again, alpha activity, but this time there was higher synchronization in the mutual gaze condition. And we looked into literature, what does that mean? Because in the previous studies, we saw higher desynchronization in mutual gaze. And what we have found in literature is that higher synchronized activity, alpha activity, means actually suppression mechanisms. So they were trying to suppress the irrelevant gaze of the robot in this case. The robot gaze in the previous gaze steering study was also irrelevant, but in that case, there was no competition. Here, participants are involved in a competition and they try to ignore that gaze, but they cannot. And that kind of suppression mechanism then results in slowing down of their decision processes because you have an additional effort at the neuronal level, which then results in prolonged responses. Now, another very interesting aspect of the study was that we could look at sort of strategies that people took during the game. And those strategies were very implicit because we asked them whether they took any strategies. They couldn't really report to us strategies, but you could analyze sequences of their responses and whether these sequences actually fell under a certain category of a strategy. So one strategy is win, stay, lose, shift, meaning if you win the next trial, you do the same. If you lose on the next trial, you do the opposite, right? Very simple strategy. And you can look at patterns of trials whether participants followed this kind of strategy. Interestingly, this is the strategy that also the robot was programmed with in 80% of trials, and this is the optimal strategy. So what you can see here is that, again, when people were engaged in the mutual gaze condition, they chose this strategy less often. And that's in occurrence rate and also in the sequence length with respect to that specific strategy. Now, having said that this is an optimal strategy, it's quite interesting because, again, mutual gaze here was impairing performance in a similar way as also in terms of response times. Participants were slower and were not necessarily choosing optimal strategy when there was mutual gaze. Now here I plotted ERPs that are locked to the offset of the blank screen. This paradigm was not specifically designed for ERPs. So it's because there's not specific events where you can lock the EEG signal to. What happens is basically that participants get to understand whether they're winning or losing in a more gradual way, because as the screen goes off, they start seeing the cars either going towards one another or one deviating, the other not. So there's not a clear moment where you have a feedback. So for example, you cannot look at feedback related ERPs, but we still kind of split this entire segment into subsegments, and you can see that there are very nice ERP effects in our signal. And the take home, this is a very complex ERP pattern. So I'll just tell you as a take home message is that what we observed is that first, what affects the neural activity is the gaze. So the difference here is between whether it was gaze averted or not, mutual or averted gaze. Then as the, let's say, story evolves, you see a mix of effect of gaze and whether you're winning or you're losing. So you start processing whether you're winning or losing. But then at the end, when you actually get the feedback, very interestingly, you see also effect of gaze as a main effect and effect of whether you won or lost. And that's quite striking because the gaze happened way, way, way earlier and still affects the way you process your feedback. So that is quite interesting to observe. So anyway, as a kind of conclusion from this study, we can say that the robot gaze again acts as a strong social signal, but it can be distracting. In this case, it's actually not beneficial for our participants, and it delays response times. It makes participants choose suboptimal strategies, and it engages suppression mechanisms, which are costly in terms of time. So when I give this talk to people who are working more in robotics, I always say that there's this trend in social robotics to endow robots with as much social signals as possible to make them social. But our study shows that social is not always beneficial. It really depends on the task. And if you want your participant or your users to focus well on their task and to actually do their task efficiently, then maybe having a robot next to them that is extremely socially engaging is not the best thing to do. But on the other hand, if you have an elderly person for whom you want to have an engaging interaction, where you want to make sure that they would, for example, follow recommendations about taking medicine, then social, of course, is beneficial. So depending on the user, on the context, on the task, I think one has to really think carefully of how much of these social signals we want to have in our robots. So that part was about joint attention, because mutual gaze is also joint attention and social signals. Now I'll move to the second part, which is the intentional stance towards robots. So very philosophical concept. And this is the title of my ERC grant. And I must say that it has been quite a pain to actually even start with this project. And the reason is that this is a philosophical concept, and it's not always easy to operationalize philosophical concepts into experimental protocols. So I don't think I need to explain to this audience what intentional stance is. We took Daniel Dennett's exact formulations, and the idea that intentional stance, people adopt intentional stance when they explain, predict behaviors with reference to mental states, and on the contrary, design stance when we predict and behavior of others with reference to how the system was designed to behave. Then the question is, since robots look like humans, sometimes humanoid robots do, they might behave like humans. When and under what conditions would people adopt intentional, and when they would adopt design stance? But before we can ask that question, as I say, the question is, how do you actually measure whether participants adopted intentional stance or not? And that's the part of operationalizing a philosophical concept. So we came up with this task that we think brings us somewhere close, but of course it's not perfect, and I'm perfectly aware that this is not a perfect tool to measure, let's say, people's intentional stance. So what people are asked to do here is they have 34 scenarios of this type. And so one scenario is a kind of a triplet of these photos. And as you see, there's a little story there told by this sequence of these three pictures. And then with each of this sequence, participants have two sentences that describe what's happening in this scenario. And participants' task is to move the slider towards the description that they think fits best to the scenario. And one description is using very mentalistic terms, so intentional terms. ICAP was trying to cheat by looking at opponent's cards. Here you see ICAP was trying to cheat. Or ICAP was unbalanced for a moment. So this is a very mechanistic description. And then participants make those choices 34 times across different scenarios with different descriptions. And then we can sort of quantify this by, let's say, assigning number 0 to the extreme mechanistic. So if participant would take this cursor to this extreme here, we would say 0. To this extreme here, we would say 100. It's just a way of coding things into numbers. And when you score the whole thing this way, what we observe is that on average, participants respond with like 40, the number 41, which is our magic number, because we observe this across many, many experiments. We have done this and replicated this magic number many, many times. So let's say population of, let's say, general population of participants scores usually around 41. What does that mean? It means that it's less than 50, so it's on the mechanistic side, right? But it's not 0, which means that there is some cases, there are some cases where there is some intentionality, or the choices are more on the intentional side. Now, what we also observed from the first study is that actually individuals differ quite a lot. So when there is a person who will be more likely to choose intentional descriptions, they will stay with those intentional descriptions. And then there are those who will choose mechanistic descriptions. And then another observation from this first study was that level of education correlates negatively with the likelihood of choosing mentalistic descriptions. So the higher educated you are, the more likely you will choose mechanistic descriptions. Okay. Now, having observed this, let's say these individual differences, we thought of something a bit crazy. We thought, let's see if we can see those differences at the neural level. So we invited our participants to the lab, and while they were doing this task, we also measured their EEG signal. So we had to adapt this task a little bit so that the sentences wouldn't be written, so that we wouldn't have too many artifacts in the EEG signal. So they were spoken auditorily. And that's how the design looked. So people would hear one description and the other. Of course, the order was counterbalanced and randomized and so on and so forth. And our question was whether we could predict from the EEG signal before they move their hand to make a decision on the slider, whether that EEG signal could tell us whether a person would be more likely to choose mechanistic or intentional description. And in fact, we could. In the gamma activity in that period, we could distinguish at an individual level. So this was not at a trial level, but we could distinguish those people. As I said, people differ. And you can distinguish those who are more likely to choose intentional descriptions as compared to those who choose mechanistic descriptions. Now, even more interestingly, this was a manipulation that we've done that we thought, like, let's try. We didn't have like much hope that it will work, but it didn't cost us much. So we tried. We measured also their EEG during resting state. What does that mean? They came to the lab, we put the cap on their heads. They didn't know yet what task they would do. They haven't seen the robot. They haven't seen any pictures. They had no idea. They just came to the lab. We said, okay, now your EEG cap is on. Just try to relax for a few minutes and think about whatever you want to think. And this is called resting state activity, neural activity, either in EEG or fMRI. And actually, we were able to predict from the resting state activity whether a given person would be more on the intentional side or more on the mechanistic side in terms of their choices. So there was something in their neural activity before they even did the task that then determined their choices in the task. Now, of course, we cannot say whether it's a state or a trait because we haven't re-invited our participants into the lab. So maybe at this particular time and that day, they were more on the intentional side for whatever reason. But it's quite interesting. And it's interesting that this differentiation we could observe in the beta activity on those regions. So we didn't know exactly how to interpret this at first. And then again, we went looking into literature and we found a paper by a group from Kai Fogelei, whom you probably know, some of you, and his co-authors, where they did EEG together with fMRI. And they found activity exactly in these regions of the EEG signal and also in beta activity that was related to mentalizing processes during resting state. So default mode network. They knew that this was default mode network because that was from fMRI. And that correlated with this kind of activity. So our results are in line with that literature and show that indeed this default mode network then predicted participants' responses to the questionnaire. Okay, so that was sort of what I told you here was it can be summed up as that humans differ in their likelihood of adopting the intentional stance, and this difference can be detected already in the resting state EEG signal. Again, I'm careful here by saying that I don't know whether this is a state or a trait, but yeah, one can see something very interesting in the neural activity. Now, what I showed you was like a sort of baseline attitude or stance that people would have when they come to the lab without any prior modulation of that stance. The interesting question for us is whether it is possible to modulate participant stance by robot behavior, let's say. One other aspect, of course, is also physical appearance, but we're not looking into that because we're using primarily only ICAB robot. So we thought, what happens when we actually make the robot behave in a human-like way or mechanistic way, whether that would up or down modulate that score, that magic 41 score. And for that purpose, we have had many failed attempts. I'm not going to talk in detail about those where we had behaviors of the robot, let's say, completely copied from human. So we had the robot having eye movements that were copied from human participants. And we wanted to see whether this kind of eye movements would, for example, modulate participants' intentional stance score. And that didn't do the trick because they were just observing the robot. Maybe they were not engaged enough. So after many, many attempts, we thought like, okay, let's do something more, let's say, gross in terms of behaviors, and let's make participants really engaged in an interaction with a robot. Let's make them do something that matters to them socially. And then we thought of what sort of activity people are doing, usually with friends, that is socially bonding, that we could also implement in the lab. And we thought of movie watching together. And that movie watching can be, you can have a situation where actually your partner with whom you're watching the movie is responding in a very similar way as you are to what's happening in the movie, or not. So this is our paradigm that we developed. So we first administer our task, this test, intentional stance test, before they have an interaction with the robot. So this is our baseline. Then they do the task. And then we administer this test again after the task. And we want to see if there will be a difference between pre and post. And the task is movie watching. In one condition, the robot will be behaving in a superhuman-like way. You will see in a moment. And it will be very reactive to what's happening in the movie. So participants, let me pause this for a moment. Participants are watching with ICAB on this screen. You see they're watching a movie. What you see here in this corner is what's happening in the movie. And you'll see, in this case, human-like reactions of the robot. So you see, this is one of the reactions that is very hard to not react as well. So most of our participants were laughing together with ICAP, and that kind of creates really a social bonding. You're emotionally synchronized, and you have similar reactions. You understand why the robot is laughing at that given moment. Then there were also other reactions. The robot was like terrified because there was a tiger attacking some other animal, or it was in awe looking at a beautiful bird, eagle, flying over Grand Canyon. So we programmed the robot to be human-like in these kind of reactions here. And then we also had a control condition where the robot was completely mechanistic. And by mechanistic, I don't have a video here, but basically it would respond. We also wanted to have sounds and reactions because otherwise we would have other confounds in the design. So the robot was also reacting, but was reacting with beeps, like a car sensor when you're parking. It would go like beep, 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 beep. And was completely, let's say, on its own without paying any attention to the human. While in the human-like condition, it would sometimes turn its head towards human. It would be much more interactive. And these are results. So what you see here is our intentional stance score before and after. And before is around our, as I say, magic number of 40. Again, this is our experiment 1, and you see that in the human-like condition, we managed to increase that score after the interaction. Now, this is our experiment 2, where we, since I couldn't believe this to be true after many failed attempts, as I told you, I thought, okay, I want to replicate this effect. So we ran experiment 2, exactly same manipulation with human-like behavior. And we replicated the effect again. So we increased our the score. And this is our control condition where the robot was very mechanical. You see no difference. So that whatever tiny difference that you see was statistically not significant. So that shows that actually you can increase the intentional stance score by robot behavior. And then we have another study that is, again, an interactive study that participants and the robot are doing the task together. So their task is to move, I'm not going to talk much about the details of the study. Basically, they need to move jointly a cursor towards a target. And one of the partners is responsible for just moving the cursor, and the other one is responsible for, let's say, confirming when the cursor goes up to the target position. So it's a joint task, and they have to do it as a team. And this is how it looks. You see the cursor is being moved by the robot, and then the participant is confirmed. This was sort of a sense of agency also experiment. I don't know if I'll have time to talk about that part. But what we observed here is also an increase of our intentional stance score after the interaction. Now, I showed you that it's possible to increase intentional stance score. The question is whether we can also decrease it by very mechanical robot behavior. So here in this task, again, a very complicated paradigm, but a fun task to do. Participants were asked to create a melodic sequence of taps. So they had a vertically presented screen where they were tapping keys, and each key was a tone. So they created a melody. Then they were teaching it to the ICAP. ICAP learned it. The learned part was a story we told them, because in reality, the ICAP was pre-programmed to just follow the taps of the participants. And then they were playing duet phase, where ICAP was supposed to be the leader, and participants were supposed to synchronize with ICAP. And the interesting part was that we asked our participants, we programmed the robot in such a way that it would make mistakes. And some of the mistakes would be very human-like, because it would just kind of mix up the two taps. And some of the mistakes were very mechanical. And you will see in a moment how the mechanical one looked. So this is already when they're playing in a duet. The melody here is, just for illustration purposes, extremely simple. But of course, it was up to participants to choose the melody. So sometimes there were much more complex sequences there. And so here you have a human-like error. So as I say, it's a very simple melody, but yeah, you can imagine it could get harder. And now the robot just swapped two taps, right? So it was by accident tapped the wrong tap. That could happen to a human, especially with a more complex melody. Now, machine-like error is very machine-like. You will see in a moment. So it gets into a loop, right? And it doesn't exit it. So it gets into a very mechanical loop, and it cannot get out of it. What we observed with this is that our intentional stance score actually in the mechanical condition dropped down. So that difference here that you see was significant. There was no change in the human-like condition. So it is also possible to down modulate the intentional stance score with very mechanical behavior. And just as a side remark, because I find it very fascinating, is that we looked, so this is not so much related to intentional stance, but I wanted to just mention this to you. We looked at other behavioral markers of let's say, social interaction among participants. And one of them is variability in behavior. So we looked at participants' variability, temporal variability between their taps. And what we observed is that in the human-like condition, they decreased variability. And decrease of variability is a marker of, it's actually signaling cooperation. So this is something that is observed in humans, but also animal kingdom. The moment you compete with someone, you increase variability because you want to be more unpredictable. The moment you decrease variability is because you want to cooperate and you want to signal cooperation to your partner. So in the human-like condition, they actually decrease their variability, meaning that they treated the robot as a more cooperative partner in their task. Okay, so here I wanted just to say that the context of this kind of machine-like repetitive behavior affects human behavior and adoption of the intentional stance. So conclusions from this part of the talk: intentional stance, interaction with the robot might actually modulate the degree of adoption of intentional stance. The kind of like me and social bonding increases the attribution of intentionality, while mechanical behavior decreases adoption of intentional stance. Now, I have an entire long section about sense of agency, and I see that I'm running out of time, so I'll kind of more quickly go through this. I wanted to explain all the paradigms that we use for measuring sense of agency, because I think it's very interesting in the context of this audience. So I'll just very quickly go through our one paradigm that we've done that was a joint action task, where participants were playing a game, this time not with ICAP, with a Cosmo robot, which is a sort of a game where you need to, again, take a little bit of a risk. It's a game that resembles a situation of when you need to take action to, let's say, prevent from bad consequences. And when this happens in a crowd of people, often nobody acts. There's this kind of diffusion of responsibility. So this is a situation like if you imagine that someone faints on the street and nobody does anything, because why should I act if there are other people who could act? And that can happen. This is a social phenomenon. So there's kind of like diffusion of responsibility and decrease of individual sense of agency. So this sort of having this in mind, this is a paradigm we have adopted. This was a paradigm developed by other researchers with whom we've worked on this. And here your task is to, when you play alone, you need to prevent a balloon from bursting. So there's a balloon, you see, that is being inflated, and then at some point it will reach this pin. If it reaches the pin, it will burst. And when it bursts, you lose a lot of points. So you can stop the balloon by just pressing a button. But if you stop too early, you lose also a lot of points. So in this case, you will lose a lot of points. In this case, you will lose very few points because you waited long enough. So you took a lot of risk, but the balloon didn't burst. And of course, if it bursts, then you lose an enormous amount of points. And after each of this score, we ask participants, how much in control did you feel over your action on a scale? So that was the sense of agency part. Now you can play this alone, or you can play this with another robot. This is a small Cosmo robot, which is like a commercial, very simple toy, basically. So now either you can act or Cosmo can act. So if Cosmo acts, you're good, because if Cosmo acts, then nobody loses points. Fantastic. But unfortunately, you never know, because Cosmo acts only in 60% of trials. So you never know whether it will act or not. You need to, again, take a risk, and sort of it's a shared responsibility situation. And again, we ask participants, how much did you feel in control of your actions? So this is how it looks there. This is our little Cosmo, and you'll see it approaching the cube where it can act. So the acting is tapping on the cube. It gets ready, it goes towards the cube. It's a very cute robot. Then our participants is getting ready as well. And now you will see on the screen the balloon inflating, you see. This time Cosmo acted great, we are safe, super. Now what we see in this task is that in the joint condition, people's subjective report of sense of agency was decreased as compared to individual. And this is a pattern that has been observed with also in human-human interaction, but has not been observed in human-computer interaction. So our Cosmo actually is closer to a human in this kind of task than a computer is. Now, in order to make sure that everything, we controlled for everything that was there to be controlled for, we also had a condition where there were mechanical pumps, so not really agentic systems. And the task was similar, but you were playing with pumps rather than a robot. And in this case, you don't see the effect when you have our pump manipulation. And then again, to make sure that we control for everything, we also had a condition where participants were playing either with another human. So you see there's a person here occluded. We needed to occlude her face because we needed to make sure that there will be no additional signals, no additional smiles, no social interaction, just the tapping. So there's a person here tapping, or so participants are either playing with a person or with Cosmo within subject design. And what we see is that the pattern is basically the same, whether they're playing with a robot or with a human. So our little Cosmo, even though it's not very human-like, but it shows very similar pattern in terms of diffusion of responsibility, task, joint sense of agency in a joint task. And that's quite interesting, we thought. So our own sense of agency is reduced in a joint action with the robot. So this is kind of like a marker that the robot is treated as a social entity, because we know that this happens also with other humans. And now my very last part that I'll have to rush through very quickly is vicarious sense of agency. So the idea that you experience sense of agency over other people's actions. And this has been found in human-human interaction, that when you observe other humans, you also sort of experience sense of agency. And with this set of experiments, this is again a very long line of research, and an entire sub-team in my team dedicated to this line of research. We use the intentional binding paradigm that maybe you're familiar with from Patrick Haggard and colleagues. I have an entire long introduction to the intentional binding paradigm, but I guess I'll just run through this very quickly. So the idea is that when you produce a sensory consequence of your action, so you press a key and then there's a tone, for example, a tone happening, the perceived timing, which is measured in a Libet clock, the perceived timing between those two events, the action and the effect, shrinks. So they are bound together, hence intentional binding, because you are the one who's producing that action. And there are all interesting theoretical accounts for why that happens. And what we have done here is we looked into this intentional binding paradigm with respect to robot acting, or you acting, or you're playing in solo or in a joint condition. So the paradigm is a bit complicated, but basically in order to look at the intentional binding effect, you need to compare baseline condition where there's only action or only tone, right? So you have only one event, and you compare those two baseline conditions, which are you see here, only action or only tone. You compare these two baseline conditions to a situation where you have action and tone. So you have action and a consequence of that action. And you ask participants to estimate on a continuously running Libet clock, when do you think an action happened, or when do you think a tone happened? So we have two possible responses here, two possible tasks, either action or tone. And then in these two conditions, these sort of estimates of the time should be linked more, brought closer as compared to the baseline condition. So I will skip through this quickly, because this is just explanation of the intentional binding paradigm. We did a manipulation with Cosmo as well, where we were interested in how much sensory motor representation of a robot matters for the vicarious sense of agency. And Cosmo was performing actions either physically by tapping, you saw on the cube or on a keyboard in our case, or we told participants that it's digitally sending a command to the computer to act. In the digital condition, you don't have the same sensory motor representation of the robot action because there's no physical embodied action present. And basically just to cut the long story short, what you observe is that when you're evaluating the tone event, when you have physical action, so the Cosmo actually pressing, you see a vicarious sense of agency. So this effect is the intentional binding effect for the robot. When you have a digital action, so no embodied action, you don't see a vicarious sense of agency, the vicarious intentional binding effect. For the action event, in the physical action, you also don't see the effect, and I'll focus on that a little bit more in a moment. For the digital action, you actually see a reverse pattern, which we can discuss later in the discussion, that has been observed also in literature for involuntary actions. Now, the interesting part is this aspect, because when you ask participants to evaluate the action event, for physical action, we don't see the vicarious intentional binding effect, but we do see a correlation with attribution of intentionality, because we asked our participants before they did the task, we asked them to fill out a questionnaire. This is a Weitz score that is a standard questionnaire very often used to evaluate the degree that people attribute intentionality to robots in general. And the more intentionality they attributed, the more they showed vicarious sense of agency but only in the physical action condition for Cosmo. So physical action matters, but in this kind of non-anthropomorphic robot, you need to boost that effect a little bit by attribution of intentionality. Now, we also have done this with the ICAB robot, and in this case, there is a vicarious intentional binding effect always observed. So it's super easy to actually see this effect with the robot, with the humanoid robot. And it's very interesting because the moment you have a humanoid shape, then you observe the vicarious sense of agency. In addition, with the humanoid robot, you also see that correlation with the likelihood of, let's say, attribution of intentionality, but it only boosts the effect because the effect is already there. So it's not really needed to see the effect. So that was a very short and quick rush through the intentional binding paradigm, but I just wanted to summarize this at a more conclusive level. So what we have learned is that if you have a digital action of a robot, so you don't have a physical sense, or it's difficult to have a physical sensory motor representation of that action, then vicarious sense of agency never occurs for a non-humanoid robot. Then if you have a physical action performed by a non-humanoid, non-anthropomorphic robot, there is there's a weak representation of the sensory motor part. So that's why you have a little bit of a mixed effect, and you need this boost from the intentionality attribution to see the effect. And then when you see a physical action performed by a humanoid robot, then you have actually a very good accurate representation at the sensory motor level, and therefore you see vicarious sense of agency emerging. So that's the aspect related to sensory motor representation of an embodied robot. Now, regarding intentional stance, the effect of intentional stance, as I already said, in terms of digital action, there's intentional stance won't help. Even if you're a person who is likely to adopt intentional stance towards robots, it won't help in terms of vicarious sense of agency. If it's physical action performed by a non-anthropomorphic robot, then you see this correlation that I showed you. So vicarious sense of agency emerges as a function of intentional stance. And then if this physical action is performed by a humanoid robot, then the vicarious sense of agency emerges anyway, independently, but it's additionally boosted by intentional stance. So this is pretty much it. As a very final take-home message from this part is that both action representation and intentionality attribution play a role in the emergence of vicarious sense of agency and human-robot interaction. And the very general conclusions from this part on social signals and joint attention, we can say that robot behavior is interpreted, especially gaze, is interpreted by humans as social, that affects our cognitive processes. From the part on intentional stance, we can say that robots might actually evoke adoption of intentional stance, especially if they are engaged in a sort of social interaction with humans. And then finally, vicarious sense of agency towards robots depends on both sensory motor representation of an action and intentional stance. So with this, I would like to thank my team, the funding agency, and thank you very much for your attention.
Okay, thank you very much. I'm going to stop the recording.